Derivation of the second order integrated rate law is similar to the first, but we start with the rate being dependent on the concentration of two reactants, or the square of one. So we can do the same kind of rewriting as we did before to get the amount on one side of the equation and time on the other. And we integrate in the same way from the initial amount to the amount at time t. And we can plot this as a linear equation if we put 1 over the amount on the y-axis and time on the x-axis. So k still shows up as the slope. It's positive this time. And 1 over the initial amount is the y-intercept. So nothing too different from what we did for the first order reaction. And similarly, we can use the fact that it's linear when we plot 1 over the amount versus time to determine whether an experimental reaction is second order. We can also use the relationship to analyze it according to the fraction, or the half-life, just like we did for first order, but we're going to find a different result. And so the half-life for a second order reaction is not a constant, and the time it takes for 1/2 of the remaining amount of material to react gets longer as the amount of material decreases. So while the half-life of second order reactions can still be something interesting in certain niche cases, it's not the useful piece of information that it is for first order reactions.